Welcome back, and now we go for the implementation of the support vector machine using the interior point method. I'll be basing these videos in this particular paper, Efficient SVM Training, using low-rank kernel representations. Okay, a paper that was published in 2001 by Fine and Scheinberg. This paper is really dense. Please guys read the paper and try at least to understand what's happening behind this approach of solving the support vector machines. You see that this is much deeper than the previous implementation. The previous implementation was just like to solve a linear optimization problem. It had like one trick I discussed with you guys that, okay, just pay attention to that book chapter, understand and read more about that particular trick. Here we have like no trick to solve. This is a complete solution. Of course, I decided to implement all the steps, but an additional one which is related to the low rank representation. So I solved the problem, the complete problem, without reducing it. That's basically what this paper brings. Like, okay, it brings a complete the solution for the complete problem, considering all points you have in your input space, and then it brings a complement in which it discusses on how to reduce the problem using low-rank kernel representations. Okay, let's start. This is going to be interesting. Here we have our primal problem and our dual problem for the support vector machine. Please, guys, pause the video here. Remember the problems. Here we had a minimization of a convex function, a maximization of a concave function. Okay. Again, here we've got a constraint that was vanished after solving the Lagrangian of our primal in order to find the dual. This C over here is also referred to as cost. It came just after the Lagrangian differentiation of our primal as well. In terms of some lambdas are defined with you guys. I'm not sure if you remember. If you don't, go back and see the other videos, okay? This is a slack variable just to bring up the possibility of having overlapping classes. I think you guys remember. And this is our cost multiplied by the total, of course, the total value of slackness we've got in our problem. That's like the overall relaxation of our problem due to class overlapping. Many people, just to pay attention to this, many people solve, like use some packages like Weka, or some packages could be like libsvm or any kind of package, and set up this cost as just use the default value. However, the default value may not work because I need to give maybe a greater importance for this cost to make possible alphas vary in this range. Otherwise, we'll not have the Karushkin-Tucker multipliers alpha I, alpha j properly defined, and my solution will not be the best solution. You know what's interesting? Some people just come up asking, oh, I decided to use the support vector machine, but the result was terrible. And I say, okay, that's possible because maybe your space was not properly kernelized, as we're going to see later. However, that might not be the case. Sometimes it's just because C was like the default value was too small and it should be greater. In case you have doubts, just use a very large number for C. It's going to take more time to optimize, but at least it's going to give your algorithm the opportunity to find values inside this range. Okay, it's going to take more time, but yeah, it's a matter of time. So first of all, we are going to reformulate those two problems in matrix form. Why matrix form? Because it's going to be easier to work with. First of all, we are going to formulate the primal problem in matrix form. Here we have the primal problem. What I'm going to do, of course, I need to come up with a different way of formulating it. Just remember something. If I have the Lagrangian here, if I decide to write the Lagrangian and differentiate the Lagrangian of our primal in terms of W, I will have W's equals to the sum of alpha I, yi, xi. You probably remember that. What can I do about that? I can proceed with some simplification, even in the primal. Take a look. I can write this, of course, as using a different way. So I can just take a look over here. Our minimization, our primal, is going to be written in a different way. We're going, first of all, we're going to distribute. Yeah, that's this step. I didn't show you the full step, just like just starting with like baby steps. So I'm just multiplying, distributing yi to all those two variables over here. So we have yi multiplied by the inner product, by the dot product, plus yib over here. And of course, I brought up all this right side term to the left, making that, of course, plus something, plus this psi I over here, as you might notice. And I decided to write this as greater than or equal to a vector of E, a E vector. This basically means a vector with ones. Okay, so it's this one, I just kept this one on the right side. I'm going to write that differently later, but this is just like a baby step. Going to the next step, I rewrote, I thought actually this was already the next slide, but it's okay. Take a look, I just wrote W as the sums, two sums. Why? Because this is inside it is a dot product with a square root, and then I have something to the square. When I cancel out the square root with these two, I have here inside a dot product of W by itself, and W by itself is this, as we've seen in the previous formulation. So I just opened up this formulation, as you guys might notice here. So instead of writing in terms of W, I'm writing in terms of alphas and y's and x's, okay? And the same is going to happen here. Instead of W, this is going to be the sum of alpha I, yi, xi, and then I can, as this is a linear transformation, I can bring the sum and the scalars outside, and that's going to be the alpha I, yj. I just called like j over here, because here I was using I to index this x, and this is going to refer to a different, of course, value for a different x, so to speak. So that's why I decided to call like xj. Okay? And then we're going to have the same over here. Okay, that's the same. From this primal, I can take like some decisions, some nice decisions, and reformulate using a matrix Q. This is going to be a matrix for me. If you guys pay attention, what is the inner product or the dot product of every vector xi by every vector xj? Every vector xi by every vector xj. That's interesting. Let's see just this product over here. If I open R, and I take, for example, iris, the data set iris as my example, we've got 4 attributes and the class. This is just the row ID, okay, the row identifier. So if I take the 4 first, which are the attributes, okay, they are here. Each one of those is a vector, another vector, another vector. What should I do? I should just, okay, this is going to be my vector or my matrix X. What is the product of one of those guys dot product by one of those guys? That's because the data type, sorry. I'm going to transform this into a matrix. I think this is going to work now. Yeah. So the dot product by the first element, the first row by itself, the first by the second, the first by the third, and so on, and up to the 150. I should do something like that for every possibility. Just pay attention. How could I do that? I could just compute X, and maybe what happens if I decide, the transpose of X product by X itself, that's going to provide some matrix for me. I'm going to call this as matrix D. Let's see how many dimensions. Ah, no, it's the opposite. Sorry, guys. Actually, it's X by X transposed. So take a look. I have every example against every example. Every dot product that a single example has in terms of the others, of all others. Remember, I've got 150 examples in my iris dataset. So this is a matrix with all the dot products. So what is nice about that is this brings the information of all dot products. If I plot this using an image, for example, you guys are going to see something like this. How similar or how different each of those elements in our space are one another. Because that's what we are able to measure using dot product. We can measure how similar or how different they are to one another. Of course, that's what we have from this product, this inner product over here. So what I'm doing with this yij is something like this. If D is this, so these y's are this, our results of iris in the 5th column, again as a vector, sorry guys, because sometimes I make this mistake. So this is going to be my y vector, 150 values. Inner product or dot product, sorry, for every other possibility given the transpose of y. This is going to produce again a matrix. Let's call it like F, could be 150 by 150. What is the Q matrix? Is F element-wise or element-wise multiplication by D. That's my matrix Q. So I can transform this into a matrix operation. That's why I decide to call this Q. It's just easier to represent, and Q will be, of course, 150 by 150, because this is going to result in a product element by element, cell by cell. Again, I can see how my Q looks like. Quite interesting. I've got some similarity. Take a look. The first class happens here up to 150. If this block has a non-homogeneous color, it means that when I compare the 50 first elements against the 50 first elements, somehow they've got some similarity because this is more homogeneous. The same happens here, but of course some elements are more similar to this, as you might notice the color. Quite nice to interpret those matrices, isn't it? This represents the last 50 elements against themselves. They've got like some level of similarity. And this, of course, if I take the last 50 with the 50 at the middle of our data set, this is the similarity. And this is against the first 50. As far as the colors are different, I can detect. Yeah, that's not important now. Okay. Going back, so I'm going to call this as Q. So if I call this as Q, what I can do is all alphas that are used here could be transformed by alpha transposed Q alpha. Wow, that's so nice. So I don't need the sums. I don't need to represent using sums. I can use matrix multiplications. Okay, so alpha transpose Q alpha, and 1/2, that's 1/2 over here, plus C, sum of something, select variables. Over here, I will have my Q matrix. So Q matrix applied on alphas. Take a look. Q matrix applied on alphas. Plus some, I can represent every vector with a single class value as a vector, actually, not as a scalar, but as a vector. That's why we have Y here in bold. And instead of having every scalar slack variable, we've got the vector here with all scalar variables, psi. Here, instead of having a single value 1, we've got the vector of ones. Take a look. Oh, that's nice. We just have the same problem in a different way of formulating, basically. Okay. Next step, we don't need, of course, anymore our vector W. That's not necessary anymore after some substitutions. There's something here. We have, of course, you guys remember, we have to make our constraint equals to 0. To make our constraint equals to 0, remember, this could be greater than or equal to 1, to a vector with ones. So if it can be greater than or equal, I should subtract something that is positive. So subtract here another slack variable, another set of slack variables to ensure the equalities, to ensure our constraints in terms of equalities. So that's why we are subtracting S over here, okay? A vector S. Nice. So this vector has to contain scalars that are greater than or equal to 0 to make this valid. Again, what can I do with my dual problem? How can I reformulate it using matrices? It's kind of easy, right? This is the Q matrix. Again, now you guys know it. It's a Q matrix. What happens with this alpha I, alpha j in terms of a sum? That's exactly the same as alpha transpose Q alpha. So every time I see like some sum of alphas and multiplied by something, that's the same as alpha transpose Q alpha. We have minus 1/2. Of course, here I can formulate with this sum, but I can also take the vector containing all alphas and multiply it by the vector with ones. Of course, this is so easy, right? This is really easy. I'm going to show it. For example, consider our alphas are like this: 0.1, 0.001, 0, and 0.2, for example. This is our vector with alphas. When I perform this product by a vector with ones, with 4 ones, what happens is a sum. That's the same as summing up the vector A. That's what's happening here, okay? And then I decided to reform Instead of using alpha I for every possibility of I from 1 to all my m elements in my training sample, I decided to use the vector alpha, whose lower bound is defined by a zero vector and upper bound by a vector of a c vector, repeating all values for c. Here I could write like an E if you guys prefer. Okay. No, sorry. Oh, sorry, my bad. It's not a one vector, it's a zero vector. Yeah, right. And here, of course, take a look. I am multiplying every value I have for alpha and the subscript I by yi. That's the same than transposing my vector y multiplied by alpha, vector alpha, and that must be equals to 0. This is quite easy, right? Now we've got both problems in matrix form. Let's take a look. Both problems are here. What can I do? What I should do next? Think. Pause the video and think. What was the next step to solve the interior point method? I think you guys remember that we had to define the barriers. The barriers are this. Every variable I have in my primal and in my dual must be rewritten in my optimization function in order to define how the barriers are going to be controlled along the iterations. Okay, let's do it. So I'm going to take this size, this vector, and as I need to be greater than or equal, and I am in a minimization problem, I think you guys remember I use minus logs multiplied by some me. I'm going to use the same me over here, okay? Log of every possibility for that vector. That's why we're summing up over here. You guys probably remember this. If you don't, go back. Of course, here S slacks, another set of slack variables must be greater than or equal to 0. Again, minus because we are in a minimization problem. Me times the sum of logs. We had the same. This is a barrier. Okay, barrier. Again. Okay, we have to bring our constraint to be part of our Lagrangian function. How that's going to happen? I'm going to make it equal to 0. So I bring this vector of 1s to the left side as minus e, and multiply this by our Cauchy-Tucker multiplier. Okay? In this case, you can also refer to Lagrange because it's equals to 0, so it's already an equality. And we are always using minus here for all formulations. Again, if you don't remember, just go to the video about the Cauchy-Tucker conditions that I discussed with you about the convex cones. And you guys probably remember that either I use always minus over here, or I change and multiply the coefficients of my objective function by -1. That's going to be the same effect. But yeah, that's fast at this point, I hope. Okay, and now I need to differentiate my Lagrangian. That's part of my solution. You guys probably remember, I need to differentiate it. How? And in terms of which variables? Of course, my slacks, S and Xi, my B and my lambda, which is my Cauchy-Tucker multiplier, or Lagrange in this case if you prefer, because we're solving for equalities. Differentiate in terms of S, I just decided to reformulate S as a matrix, as a diagonal matrix here, because it would be easier to compute the inverse. Okay, but we're going to see. In terms of S, what is it? Oh, S happens here. So what I need minus me multiplied by 1 over S. 1 over S, if I want to deal with this in terms of a matrix, I could just compute the inverse of S. That's why I use a diagonal matrix here. This is going to be a diagonal matrix, okay? I'm computing its inverse. Minus me multiplied by the inverse of S. That's a solution for every possibility of derivative or log of every Si from 1 to n. Plus what? I am computing some minus S multiplied by minus lambda. That's going to be positive lambda equals 0. So me must be equals to S multiplied by lambda. This is the complementary slackness. Take a look. When I multiply this diagonal matrix by lambdas, by the Cauchy-Tucker multipliers, I will have my gap. That's nice. My gap me. When I differentiate in terms of B is here. Take a look. What I will have is y multiplied by lambda, of course, negative. This is going to be equal to 0. Okay. And differentiating in terms of size, I will have here C multiplied by some size. So differentiating in terms of all those, I will have C. That's why I have C here. And differentiating in terms of log of psi I will have, of course, minus me multiplied by the inverse matrix. The inverse matrix, diagonal matrix psi. Minus lambda, because lambda is multiplied by positive psi. Okay? You can see this as the vector. So minus lambda equals 0. And differentiate in terms of lambda, I will have, of course, my constraint. My constraint is here. Okay? Equals 0. It could be, I could add like minus over here if I prefer, but it would be, of course, equals 0. I can multiply both sides by minus 1, so it's going to be the same as my constraint. Okay? I need to do the same for my dual. Take a look at my dual problem. I will have one constraint. That means that alpha must be greater than or equal to 0 when I look at this side. That's the same in maximization problem. That's the same as doing what? As doing me plus me multiplied by the log of alpha I. On the other side, wow, A must be smaller than or equal to C. What I should do at this point? I can bring this alpha to this side and make 0, 0 smaller than or equal to C minus alpha, because I have the barriers always defined in terms of 0. When I have 0 smaller than or equal to C minus alpha, I can solve my log as C minus alpha. And that's what we have here. Our barrier for the let's call it this, some virtual point 0, because 0 is smaller than or C minus alpha brought up to the right. So I'm decomposing this inequality into two inequalities to solve it and plug the barriers, the barrier terms, as you guys might notice. And finally, this is going to be multiplied by some Cauchy-Tucker multiplier, if you prefer Lagrange multiplier, because it's for the equality. Minus beta multiplied by this. And there you are. So now we go for the differentiation. Differentiating in terms of alphas, in terms of betas, we are going to have, of course, E transpose. It's going to be a vector of ones, sorry. And differentiating now in terms of, wow, here we've got two alphas. We're going to differentiate in terms of one of those. So we're going to have what? This is the same as alpha to the square. So that's why this just is transformed into 1. So minus q alpha, as shown here, plus me multiplied by the matrix alpha inversed. It's a pity because I tried to make this in LaTeX, like to show it with a bold alpha, but I think the set of the fonts I was using were not like the best. to make this alpha like uppercase, but it's a matrix, okay? A diagonal matrix in this case. So that's the solution. And then differentiate in terms of alpha over here. Take a look. I will have what? I have me, of course, multiplied by the 1 over minus alpha I. 1 over all this, sorry. Because I have to differentiate in terms of all that is inside. So this is going to provide some, of course, this minus, okay? Inverse. And because at the end I need to differentiate internally by the chain rule, this is negative, so this becomes okay. And here, differentiate in terms of alpha, I will have, of course, beta y, vector y equals 0. And differentiate in terms of beta, beta happens here, I'll have my constraint, it's minus my constraint, but it could be plus because I could multiply both sides by minus 1, okay? The same happens here. Take a look. Now we observe the stationary point found using the primal and the dual forms. At the end, this means, guys, that's all you need to consider to find the IPM solution. That's all you need. You need all the differentiations in terms of the primal and the dual problem to solve your interior point method using an approach called the primal dual path following algorithm, as we discussed in previous classes. So I need to consider everything. You guys are going to see that there are like many similarities over here. Many similarities. I can just connect those qualities. Let's take a look. Let's consider how they could be connected to avoid, take a look here, redundancy. Okay, so lambda is the same as alpha because this must be equal to 0. Take a look. Oh, so nice. So this lambda is the same as alpha, but of course, if I bring this lambda to the other side, it's going to be an inverse of lambda. That's why this is an inverse of alpha, okay? That's the first step. Next step, S is the same as everything together. Why? Because S is going to be equals to me multiplied by the inverse of lambda. So all this together is S. That's nice. So I can change something in my formulation. My xi is going to be this. Take a look. If I have Q alpha plus something that is S, this is S, right? And if this is E, it happens here. Okay, here is negative. I could multiply both sides by -1. You guys remember, right? And here I have like, wow, B and beta probably are the same. Oh yeah, I'm gonna see that in the next slide. But psi is equal to all this, just because of the connection we are making. This connection we are making actually in between the prime and the dual spaces is actually what the complementary slackness does. We are just ensuring that the solutions will respect the same variables and constraints from both sides. So this is going to be psi. So having lambda equals alpha, this is our problem. Now we have just this problem to solve. So instead of having 1, 2, 3, 4, 5, 6 equations, actually we just have 4. Of course, this problem is more complex than the other problem we were solving together for the linear optimization. Linear optimization problem. How can I solve this? You guys know how to solve it. We need to apply an algorithm that iteratively solve it for all those equations to be equal to 0. I have to start with some value to give importance for my barriers. I cannot just solve like for me equals 0 because I could cross the barriers. I think you guys remember that. So our next step is I need to differentiate this to find my Jacobian matrix. Remember the Jacobian matrix? I think you guys remember. So if I take this equation and differentiate in terms of alpha, in terms of beta, in B, sorry, in terms of S, in terms of psi. Oh, actually, I just adapted here. I just considered, yeah, it was vanished actually, beta, because beta was the same as this YB. And I told you guys in the slides, but I didn't have like an additional slide to show it. But yeah, at least I told you. So I differentiate this first equation in terms of alpha, B, S, and psi. That's my first row. Second row is the second equation in terms of alpha, B, S, and psi. Third equation in the third row, and fourth in the fourth row in terms of all my four variables. Of course, this matrix has to be a square matrix. Take a look. I have 4 variables, 4 equations. But this goes further. You're going to see now. Now I need to multiply and make the product of this Jacobian by the deltas. You guys remember, delta alpha, delta B, delta S, delta psi, making that equals to minus f of alpha, f of B, f of S, f of psi. All my f's. Remember, for some initial point, for some initial solution. Okay. Now implement this primal dual path following interior point method to solve the support vector machine. Instead of solving, as we did with the previous IPN problem, now we're going to use a solver. So I'm not going to solve it like manually, like iteratively, but using like without any solver. I'm going to use a solver. It's just faster. Okay, it's going to perform, of course, the row reduced echelon form to reduce my matrix and everything. That makes it easier to solve my system of equations. Of course, this is necessary because my problem is more complex, because, of course, if I decide to solve it manually, it's going to take like more time. But even though I use the solver, that's all I use. So it's going to be, we're going to see the support vector machine solved in every detail. That's so nice, guys. Okay? So this is the problem I need to solve. Remember, this is just to remember, Q is actually my vector y dot product with my vector y transposed, my matrix X with all input, with the input space, dot product by my matrix transposed. We did this together. I think you guys remember. I did actually here using R, right? Okay. Our matrices, our variables S, alpha, and psi will be diagonal matrices because that makes easier to compute the inverses and everything. Just easier. I just decided. That was my decision, actually. After trying to solve it. This is something I need to tell you. The Jacobian matrix, again, has to be a square matrix. If it has to be a squared matrix, I need to be sure it will be a square matrix. Here, I just considered something. Consider I've got 200 input examples. If I have 200 input examples, when I compute the matrix Q, that will be 200 by 200. Why? I have 200 labels, and y multiplied by transpose of y will provide a matrix 200 by 200. Which is element-wise multiplied by x transposed. That means x transposed is going to be 200 by 200 too. So when I multiply element by element, I will have q as 200 by 200. This is our vector y with all classes as a column vector here. This is an identity. Take a look, this was the differentiation, minus identity. So minus identity, it's going to have like minus ones over here. This is 200 by 200. Pay attention on this, please. This is identity matrix 200 by 200. You guys may ask, why 200 by 200 here, here, and here? I'm going to tell you. Just a few moments, please. My vector minus y, it is transposed. That's why it happens like this in a row, okay? All the other elements here are zeros. And here I have my S matrix, which is a diagonal matrix with slack variables. How many variables? 200 by 200, because I have 200 values in the diagonal. Remember, 200 values in the diagonal. That explains why this matrix is 200 by 200. Why? Because take a look here. Q is going to be multiplied by delta alpha, y by delta b, minus y, minus I, sorry, the identity, negative identity matrix by delta S. So this delta S is going to be what? A diagonal matrix with, actually, it's going to be a vector, actually, with 200 elements. As it is a vector with 200 elements, this has to be 200 by 200, given it is a minus identity matrix. And as this is a vector with 200 elements, this S being used here will have 200 by 200, alpha 200 by 200, minus psi 200 by 200, and C minus alpha 200 by 200. There is a rule here. If I have n elements in my input space, in this case, I decided to define n equals to 200. 200 input examples in my space, 200 training examples, 200 training instances for my problem. My Jacobian matrix will have 3n plus 1 by 3n plus 1 elements. Remember, n equals 200 plus 200 plus 200, 3n. Plus 1, because I have one additional column here. Here, 200 plus 200 plus 200 plus 1, that's going to be 3n plus 1. Why this is necessary? Because this matrix has to be, it must allow inversion. Why it must allow inversion? Because I'm solving some system here that requires this matrix to be invertible. So in order to make it invertible, I need to ensure that this matrix is at least a squared matrix. That's why. Okay, guys, it's quite interesting, right? Of course, here I have delta alpha, I have 200 values for alpha. That's why the column space of this matrix Q, actually all these elements will be multiplied by delta alpha. All this column will be multiplied by delta B, which is a single value. That's why it's a single column over here, up to here, okay? This is a block with, of course, 3n plus 1 rows and 200 columns multiplied by 200 elements. And this is, of course, this block of 3n plus 1 rows and 200 columns multiplied by 200 values to result into those guys over here. That's why we have this Jacobian matrix like this. If you don't remember, you haven't studied about Jacobian matrices, go back to the calculus book, please, guys. Go back and study. That's really important. What is the importance about the Jacobian matrix? It tells me the direction of gradients. Take a look. If I am differentiating here, if I'm differentiating the Lagrangian, it tells me how much I can walk in every direction in terms of, consider this as an axis in my space, in terms of every alpha, all alphas, all B, that's a single value, all slacks S, all slacks psi. Very nice. I haven't told you about this differentiation here because this is so easy at this point. I think you have no problem to perform the differentiation in terms of these guys over here. It's vectorial calculus, okay? It's easy at this point. Okay, having the Jacobian matrix, what I need to do is Jacobian matrix product by my vector delta, I here called delta x, but of course inside it I've got 200 alphas, 1D, 200 s, and 200 xi's. Why 200? Because I just decided to have 200 elements in my input space as a toy problem to explain to you guys. Inside I have F1, F2, F3, and F4, minus of course all those F's, okay? So I need to, of course, what about my results? If I multiply something that has 200 by 200 by something that has 200, this is going to be 200 by one column. By one column. This is going to be the result over here. Why by one? Remember, this is a matrix, square matrix, 3n plus 1 by 3n plus 1 times 3n by 1, because this is a single column. So as it is a single column, this will have a single column, but the rows will vary. 200, 1, 200, 200. That's obvious, okay? So now we need to proceed with our solution. We need to come up with an initial solution for alpha with feasible values. That means alphas must be greater than or equal to 0, and of course, smaller than or equal to C, as you guys know. Xi, of course, define some values for Xi, define initial value for B, define initial values for S in terms of alphas and Xi's and B's. So that's all I need. I need to come up with feasible values, and then I can solve my problem. Just to give you this, guys, just download the paper. This paper by Fine and Scheinberg, read it. It's really important that you guys understand this solution. Okay, I just opened up the solution. Those authors do not provide the code. I wrote the code. We are going to discuss together. But of course, read the paper. It makes everything easier to understand what happens here. Okay, the paper has like 24 pages. Actually, I used it like I don't remember but the first 12 pages, maybe the first 10, 12 pages. The rest I didn't, because that was like just an optimization of the whole solution. So just to make sure, this paper proposes this method we saw as the basis, which is then modified to provide better results. Actually, not better, but faster results, I should say. Okay. Part of the improvements that the paper brings in its second part is how to compute the step in the direction of the solution, just to make it faster. It considers a predictor-corrector step to improve results. This is actually to improve results in terms of the gap, in terms of the primary, the dual space. It also reduces the rank of matrix Q. So instead of using the full rank matrix, they just reduce it to have like a small problem, a small at least problem. Okay? That's all for this class. Next class, we go for the implementation. See you guys.